we go, you guys. We're gonna be doing Unit 4 pressure measurement stuff. Let's see now. Hopefully this is, yeah, it's right side up. That's good. As promised, here's our little video for Unit 4, the problems in the lectures. Problem number 1. It's on page 16 of 18. So this one will be quick, hopefully. I'll draw it out here. What do we have? Got this lovely little pipe, and we've got this tube coming off of it. Goes down, around, up, bloop, 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 bloop. We've got this, so calculate the pressure at point A they want. Here, I'll get my other little points here. So the water is all within the tube here. Where does it go down to a certain point here? And then we've got another fluid that we're measuring in here. So we've got the fluid that we care about, which is water, and the manometer fluid, which is mercury. It's labeled the points here, just so we've got it. A, or that's where we're trying to measure the pressure in. 2. Got another point here. 4, it's in the elbow. We got another point here, 3, which is that interface between the water and the mercury. And then we've got another point 2, which is directly across from point 3. And then we've got the top of the mercury here at 1. So this part here, this tube here, is air at atmospheric pressure. Makes our life a little bit easier. And the mercury, it's got a specific gravity of 13.54. Okay. So we're trying to find the pressure at point A. Remember in the notes there it says to start at a known point, work your way backwards, or whatever the case may be. So the base fluid that we care about, remember we talked about the annotating what the fluid is that we're looking for the pressure. So F, it's water. It's a little bit clearer than collaborate, isn't it? And we've got in the manometer, it's going to use that base of M. That's the fluid in the manometer. And it's mercury. Mercury. Not to be confused with Freddie Mercury. So you're going to assume the water is at 4 degrees C, right? So the unit weight of the manometer, the mercury, so subset M, it's going to be that specific gravity times the unit weight of water at 4 degrees C. So 13.54 times 9.81 kilonewtons per meter cubed. Calculate that out, we get 132.8 kilonewtons per meter cubed. And then you know the unit weight of the fluid, again, because we're assuming it's water, it's 9.81 kilonewtons per meter cubed. Good. We're going to make this like, we need to find a datum, right? So we're going to look at this point here. This point, I'm going to call it 0.5. It's not on the notes, but hey. It's just in line with this pressure at point A, which is what we're interested in. So the datum is right at point A. Let's wrote datum in a very messy way. Okay. So we're trying to find the pressure. Remember, pressure equals unit weight times height. we're going to set that. So we've got our 0 here. So equals Z equals 0. Oops, you can't see that. Push it down a little bit. Okay. Which is at 0.42. So A, 4, 5, they're all at the same datum. So pressure at 5 is equal to 0. Gauge pressure, not absolute pressure. Okay. 0 kPa. That's a known thing, we know that. What else do we know? 0.1, and at 0.1, pressure at 0.1 is 0 kPa too. And that's, what's this height difference here? So this difference between our datum and 0.1 is 0.15 meters. But remember, our datum is 0. So at Z equals 0.15 meters. Just trying to think of how to draw this out here so that you can see it. So that's 0.1 to 0.2. What's that difference? 0.25 meters. Those are the only points that we have. So we're going to just pretend that down is positive. So that's what that's showing. Down is positive. It's our datum. We can do what we want. So, like I said, you start at your known point, you work your way down. So we'll start at pressure at 0.2. Pressure at 0.2. Z is equal to 0.15 plus 0.25. So 0.4 meters. So the change in pressure is that specific weight times the height. So we're dealing with mercury at 0.2. So, and it's mercury. So we've got 132.8 kilonewtons per meter cubed times 0.4 meters. Oh, change in height. So this will be Z at 0.2 minus Z at 1. So 0.4 minus 0.15. Yep. Just taking a little gut check there. So if you follow this through, you get 33.2 kilonewtons per meter squared. So kPa. Yep. So the same fluid is at 0.3 too. It's all still mercury. As 0.2. This was a change in pressure. Pressure at 0.2, just to be clear here, it's going to be pressure at 0.1, which was 0, plus this the change in pressure. So it's 33.2 kPa, just to be explicit about that, okay? What do we have? So again, back to this 0.3 and 0.2. It's the same material, it's that mercury. red in my drawing and green in the figure there on page 16. So what do we have? Since we have fluid, so at point 3, at pressure at point 3 is equal to the pressure at point 2. So 33.2 kPa. That's within the mercury, right? If we're looking at just above the mercury, it's slightly, it'll be the same-ish. Slightly different materials. Okay, I'm gonna flip the page here because we're gonna be looking at point 4 now, because we've got 1, we got 5, we got 1, we got 2, we got 3. Now we gotta find point 4 here. So that's what we'll be doing. At point 4, fling. What do we have here? The datum, let's see, this elevation at point 4 is equal to the elevation at A, which is all equal to that 0 meters, right? Because that's where we made the datum. And the fluid in this bit is water, so between 3, 4, and A, it's all water. So, and remember we said down is positive, so now that we're going up, it's going to be negative. Okay? So that change in pressure, again, is going to be the specific weight times the height, which is the specific weight times, well, the change in height, really. So that point at Z4 minus the Z at point 3, that datum. So what do we have here? 9.81 kilonewtons per meter cubed, because it's water. I'll put a little W there so that you know it's water. Water. Or could be fluid, right? Because I think we said sub-base fluid. What you're interested in, okay? Times, what do we have here? 0. Set at 0 minus, what's that, to 3, so it'll be that 15 plus 0.25, so minus 0.4 meters. And that's where that negative comes in, right? Going negative, because down is up and up is down. So we follow that through and you get negative 3.92 kPa. Therefore, at the pressure at 4 is going to be equal to the pressure at A, surprisingly. Same fluid, same elevation. So it's going to be the pressure at 3 plus this change in pressure that we just calculated. So what was our pressure at 3 that we had? Is that 33.2 kPa plus negative 3.92 kPa? And what's this equal to? 29.28 kilopascals. So we found the pressure at A. Like these are, and again, these are all gauge pressures. We wanted atmospheric pressure. Remember that, just add that 101.3. So that was the first question. So the second question, 17 of 18. Flip the page here. Calculate the difference in pressure between points A and point B of the differential pressure manometer given below. Okay, so here we go. I'm going to draw this out. You should have it out there. Start getting a little bit crazy here. We've got our lovely little pipe, and then tube that comes out, goes down and around and up and around down and around, and then it comes out in another little pipe here. What do we got? 3 different fluids in this one, so this is going to be fun. Oh. Get my other little blue marker here. What do we have here? So we'll use blue for water. So we got water in this first reservoir, first pipe, and it goes down to a certain point. And then what do we have? Mercury. I'll use green, we'll keep it the same here. Down here, this is filled with mercury to a certain point. And then it's filled with water again. This is fun. To somewhere up here. And then we've got some more mercury. Bloop, 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 bloop. Bloop, 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 bloop. And then it's somewhere in here, it changes to oil. I don't have orange, I have red, so this is what you're getting. Okay. So then red, all this oil in this second sort of pipe and reservoir. Well, this is going to be fun. So we'll go back to black here. What do we got? Point B in here. This height of water in this pipe is 6 inches. And then didn't draw to scale. So the difference between the elevation of the bottom of the water, first water set, and the top of this water is 6 inches as well. What else do we have here? So bottom of water to the top of this mercury, 10 inches. And then from mercury to the change in it between the mercury and the oil. What's that? That's 8 inches. And then from here, boop, 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 this is 6 inches from where the interface between the mercury and the oil is. We got another point here in A. So what else is this question telling us? We've got water at 4 degrees. We're going to have mercury. Its specific gravity, they tell us, is 13.54. And for oil, its specific gravity is 0.90. So calculate the difference in pressure between point A and B. B is a little bit higher than A. Not that you can tell by my lovely little drawing, but there it is on page 17 of 18. So, what's 0 degrees C is, because this is all in inches. What's that at? 39 degrees Fahrenheit, is that what that is? Gross. Okay, so here we go. Let's go figure out, we're trying to find pressure, right? Pressure equals specific weight times height. So let's go try to find our specific weights of things. So the specific weight of the mercury is equal to the specific gravity times the unit weight of water, and for this way it's imperial, so 62.4 pounds per foot cubed. Follow that through, and we got 844.9 pounds per foot cubed. Good. So what do we have here? Let's start label. Oh, wish I had a different color now all of a sudden. How we're going to label these. So we'll call this little interface point here C. We'll call this little interface point here D. I'll bring it into focus here. Beep. We're going to call this point here E. A, B, C, D, E. And then this will be F. I guess we could have called them 1, 2, 3, 4. But there it is. We'll find the unit weight of oil. So 0.90 times 62.4 pounds per foot cubed. We work that out, we get 56.2 pounds per foot cubed. Now we'll call, because we're interested, well, who knows, we'll call this point, we'll set our datum at B equal to 0, and down is positive, because this is all below. I guess we could have set whatever works in your head. We'll just do it that way. Okay. So we'll start here at point B and then we'll go down to C. Okay. So at point C, what's our elevation at point C? It's going to be 6 inches. All this stuff's in feet, so let's put it in feet, so half a foot. So our change in pressure at point C is equal to the unit weight times the height. Again, Z, what do we got here? Z at point C minus Z at point B. This is water in this chunk. So we're going to have 62.4 pounds per foot cubed times 0.5 feet minus our datum at B, right? Because that's where we forced it, so 0 feet. We work through that. What do we get? 31.2 pounds per foot squared. So our pressure at C, and remember we're trying to find the difference between B and A. It's going to be the pressure at B plus this change in pressure at point C, 31.2 pounds per foot squared. Okay, and we don't know what the pressure is at B. We're just looking for differential pressures. Okay. So let's move on. We're going to go from, so we found that, sort of, relative to B. Got pressure at C relative to B. Now we're going to go to D, this other little interface between where the mercury and the second set of water is. Okay. So at point D, there we go. Okay. What's our Z at D? Our datum here. We have compared to where at B is 0, so we've got 6 inches plus 6 inches, so 1 foot. So trying to keep everything in feet. So that change in pressure is equal to that unit weight. We're in mercury right there. Times the datum at D minus the datum at C. So what are we using here? What did we have? Unit weight of mercury, 844.9 pounds per cubic foot times one foot minus half a foot. Work through that. And we get 422.45 pounds per foot squared. So the pressure, looking good. So pressure at D is equal to that pressure C plus 422.45 pounds per foot squared. Now remember this pressure at C, it was just in terms relative to pressure at point B. Okay, so I'll move right along. At point E, which is, what do we say it was? Flip, flip. E is this point here, that interface between that second piece of water and that second bit of mercury. So its datum, like relative point at E, it's going to be, let's have a look, see. It's 2 inches. What do we have here? Yep, so 6 minus, well, 8 minus 6. Hopefully you can see that. Which is equal, you divide this by 12 to get into feet. So 0.176 of a foot. Change in pressure then is going to be that specific weight of point E, we're in water. So water times the datum at E minus the datum elevation at D. So 62.4 pounds per foot cubed times 0.167 feet minus, what did we say it was at D? 1 foot. So if we work that through, this is going to be negative, right? Again, going down and up and up and down, right? Down is positive and up is negative. So that makes sense. We're going to have a negative change in pressure, 52 pounds per foot squared. Get it? So at point E, pressure at E is equal to that pressure that we found at D, well, lowercase. Let's start again, uppercase, D plus this change in pressure, right? So pressure at D minus 52 pounds per foot squared. Again, this will all be relative to point B, which it's not really known. So last but not least, pressure at point F. Flip over here. This point F, this interface between the mercury and the oil. flip the page. Whoop. So pressure at point F. What's our elevation with respect to the datum? At point F. It's going to be that 2 inches that we found plus that 8 inches, so 10 inches. Again, we got to make it in feet. So 0.833 feet. Change in pressure equals the unit weight of the oil. Remember, because we're in the. Are we in the oil? No, we're in the mercury. Times that datum at elevation at F with respect to the datum minus where we were at E. So what's our unit weight of mercury? 844, is that right? So 844.9 pounds per cubic feet times 0.833 feet minus 0.167 feet. Work this through, and we get 563.27 pounds per square foot. So what do we got? Pressure at F is equal to pressure at E plus this change in pressure, so 563.27 pounds per foot cubed. So last but not least, point A. So that's labeled in the drawing there, so that's in that second pipe. So the elevation of A with respect to the datum is what? Four inches? 2 minus 2, there it is, 4 inches, which is equal to, hopefully you can see that, so that'll be, so you got that 6 inches, the difference between that 6 inches and the 8 inches is 2 inches, and then another 2 between that 6 and the 8, second 6 and 8. So 0.333 feet. So change in pressure is going to be, where are we in? Water. So the unit weight of water times difference between A, datum between A and F. We got 56, oh no, sorry, this will be the oil, we're in oil. So 56.2 pounds per foot cube times elevation at A, 0.333 minus 0.833 feet. And again, we're moving up, so that it's going to be negative, right? We get negative 28.1 pounds per foot squared. So the pressure at A is going to be the pressure at F minus 28.1 pounds per foot squared. So what's the point? The point of this is we're trying to find the difference between points A and B. So the difference between point pressures at point A and point B. Whoopsie. There you go. Is equal to what's our pressure at A? What's that pressure at F? Minus 28.1 minus point pressure at B. So what do we have here? We got that pressure at F minus 28.1. And we figured out what our pressure at point B was way back here. Hold on, let me flip. There's D, there's E. Here we go. You can just take this one, rearrange it. It's the only one we've got, right? So pressure at B equals 31.2 minus pressure at C. So we'll substitute. Is that right? Nope. Pressure at B equals pressure at C minus 31.2. Yep. Again, pounds per square foot. So we'll stick this expression, pop it in there. Flip, flip, flip. Here we go. Minus pressure at C minus 31.2. Pressure at F minus pressure at C. Plus that, minus that, plus 3.1. Again, this is all going to be in pounds per foot squared. Pressure at F. Again, we went and found that out. So pressure at F is equal to that pressure at E plus 563.27 minus pressure at C plus 3.1. Where do we get this? From here. Let's not keep folding it over, because I have a feeling we'll be doing this a lot here. Flip, flip, flip. So we work this through. Pressure at E minus pressure at C plus 566.27. Pressure at E, again. What's our pressure at E? Pressure at D minus 52. So what do we got here? Equals pressure at D minus 52 plus, oopsie, minus, can't forget that guy. So again, pressure at D minus pressure at C is equal to plus minus 514.27. Again, we got this pressure at D. How do we find that out? There it is. So pressure at D is pressure at C plus 422.45 minus pressure at sea plus 514.27 is equal to, oh, look at that. Would you look at that? Boop, boop. Finally something crosses off. Okay, so that plus that is 936.82, and remember this was in pounds per foot squared. Okay, so what do we know? So therefore, pressure, the difference between pressure A and pressure B, pressure at A and pressure B is equal to 936.82 pounds per foot squared. Now, if you care, I mean, this is an acceptable answer, but if you wanted to put it in PSI, so we've got 936.82 pounds per foot squared times 1 foot squared over 144 inches squared equals to 6.5 pounds per inch squared. So 6.5 PSI. People like PSI. So what does this tell you? Let's have a little thought. Let's think about this for a second. The difference between pressure A and pressure B is positive 6.5 PSI. So the pressure in A has got to be greater than the pressure at B. I'm not asking you that, but you know, just think about it for a second. So what do we got here? That's it. That's it. 1, 2. Well, this is interesting. So there's some extra questions in here that aren't necessarily in the handout, but I'll do them just because they might help you with your assignments. And why not, eh? We'll do some extra ones here. So problem 3, we're going to find pressure at A. It's a slightly different little vessel here. We've got a reservoir here. And there's a little pipe that goes down, backing up and over, and up. And it is, you'll see this symbol too. It's just means that it's open to the air. That's all. Like there's a fun little kind of cap, but that's it. So we've got this reservoir is full of water, somewhat, in here. So this is all filled with water to a certain point up in here. Boop, 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 boop. It's pressurized in here, so it's at some sort of Pascal. Got a point A in here. And we've got a point B up here. And this elevation difference between this top surface of the water in the vessel and the top of the water in the tube is 6.8 meters. And they want us to find this pressure in the vessel, okay? So it's not exposed to the atmosphere. This vent, again, it is exposed. So when you see this, you know what this means, okay? So it's either, it's usually just drawn like that. Okay, the pipe is open-ended. So we're trying to find the pressure inside the vessel. So here we go. Okay. The pressure at B is equal to the atmosphere, which is 0 gauge, right? Am I spelling this right yet? I don't know. You know that it's water. Oh, this inches, sorry. Inches, not meters. Inches. Okay. So the unit weight of water at 4 degrees C, or what was it, 39 degrees Fahrenheit, is 62.4 pounds per foot cubed. If we wanted to make it in inches, because the height is in inches, why not, eh? So water equals 62.4 pounds per foot cubed times 1 foot over, you can do it like 12 and then cube this, or say you're a nerd and you remember these things off by heart. 1,728 inches. 0.03611. That crosses off, that crosses off. We get pounds per inches cubed. 0.03611. Okay. So again, the pressure at A like, I mean, you'll probably see this in some notes. It might be in the book there too. They call this A prime. So it's the elevation of the water column in here. In the water column, it's sort of like the difference between being on the surface of the water and being just below the surface of the water. So that's what this A prime is, just pretending like you're just below the surface of the water, like you're a particle, right? You're not anything more than that. So let's pretend we're the particle in the water at this point here. It's going to be equal to that unit weight of water times the height, or that elevation difference. And we're doing this all in inches. So 0.03611 pounds per inches cubed times that height, which was 6.8 inches. Yep. Inches, so we're going to come out in pounds per inches squared, or PSI. And what do we have? 0.246 PSI. And because we're the same, right? That pressurized equals the A prime equals 0.246 PSI. So inside this vessel here, it just means that it's been pressurized. That allows that water to rise to this height, basically. So it's pressurized 0.265 of PSI. That's bonus question 3. Ready for bonus question 4? This is one of those inclined manometers that are talked about in the notes. What do we have? We got a vessel. It goes down to a pipe. Ooh, I get to use my ruler now because we're on this inclined manometer. Boop. Boop. Okay. And this is filled with some sort of fluid. So we're going to find some sort of fluid. Let's do green. Why not? Change it up. Up to a certain point, this water or this fluid raises to some elevation. Again, inside the vessel is pressurized. You gotta find this pressure in here. This angle is 15 degrees. Okay, so the specific gravity of this fluid is 0.87. I guess we could go through the back of the book and try to figure out what it is, but they tell us already. Point B here. So we've got this length. It's all on the same plane, right? So this length here is 115 millimeters. And it's vented to the top. So here we are at B. B, pressure at B is equal to 0. Because it's at atmosphere. Atmosphere. So remember the height in this incline manometer is equal to the length of it times the sine of theta. And the pressure at A is going to be equal to the height times the specific weight of whatever this fluid is. The gauge fluid, it's this subset G. So we're going to have length times the sine of theta times the unit weight of the gauge. So we can do this all at once now, I think, by now, right? So we're going to do 0.115 meters times the sine of 15 degrees meters times the specific gravity times the unit weight of water, which is 9.81 kilonewtons per meter cubed. So we got meters cubed, so this will be meters squared. We're going to come out in kPa. If we calculate all this out, we're going to get 0.254 kilonewtons per meter squared. So 0.254 kPa. Let's check, was it actually in here? Yeah, I don't know where those problems are, but hey, here we go. The joys of watching these videos. So another little thing to note here too is the cross-sectional area of this reservoir, this square. It's a lot bigger than this, although my awesome drawing isn't showing it. But in reality, you can imagine you've got a reservoir of fluid. In this case, I don't know, some sort of oily thing, and it's going through a tube. So this reservoir is going to be, the area of this reservoir is going to be a lot bigger than the area in this tube. So even if this level of water in here, this height of water, if it drops a little, this length is going to increase quite a bit. So it drops very little for every increase in this length. 2b, this length changes. So you can ignore this drop and measure as it's shown. Again, that's like that difference between areas. Okay. So again, they're not in, for some reason, they're not in the notes, but you know, some bonus questions that might help you out with the assignment. And I will post the assignment, number 2. I think it's number 2. I'll just check. But I'll keep you posted on D2L. Okay. So that's for all the equations that are in, and a couple more bonus ones in the unit 4, pressure measurement.